So what I will do now is I will just recall from last time. So what did we do? We were just we had this concept of sampling without replacement. So that was the first time we discussed sort of dependency across trials. And then in this context, we saw the hypergeometric distribution. There was a, let's assume that we had a m less than r less than n, just to make it simple. So this would be hypergeometric distribution of r. I wrote it reversely last time. And n people are there. R of them are characteristic red, let's say, and you're choosing little n people. And you get this hypergeometric distribution, which was supposedly in the following form. That is, S is from 0, 1 up to m. You could choose up to n people of characteristic R. And the chance of choosing k people of characteristic R is going to be equal to R choose k, n minus R choose m minus k, and the whole thing divided by the number of ways you could choose m people from capital N with n choose m. That's where we were at last time. And I had sort of contrasted this with one thing. I had contrasted this with sampling with this sampling without replacement. So sampling with replacement I had started before itself. That was that when you put the person back in the population, and this is what we had done before, and this corresponded to Bernoulli trials, independent. I had the crucial property of independence, and that's where the two things differed. So now let me just play with this formula a little bit. Let's start for today. So this formula, what happens is that you can rewrite this formula in the following form. Right? This is this r factorial by k factorial. Let me write it down. This formula is equal to r factorial by k factorial. Then you have n minus r factorial by n minus k factorial. And then you have two formulas. You have an r minus k factorial for the first one. And then you have a 1 over n minus r minus of m minus k factorial. And the whole thing divided by n factorial, n m factorial, and n minus m factorial. So at the bottom. So if you rewrite this a little bit, so what will you get? You stay a little bit. So you can look at, let's look at. So there's an m factorial at the bottom. So that I'll write that in blue. So green, let's say. So I'll just take this. So it's m factorial divided by, I'll leave the k factorial as it is, and I'll leave the m minus k factorial as it is. So these three terms I'll take as it is. And the rest of the terms, what I do is, I look at it. So I have r minus k factorial and r factorial. So from these two people, let me take, let me call it as red, let's say. Let's take this and this. I take these two guys. And what do I get? I get r into r minus 1 all the way up to r minus k minus 1. Right? So maybe I'll do to the next line so it's easier. Select that. This here. Erase this. So if I do that, so I'll rewrite this in red, so it's easier. Erase this. That's the red part. So that's equal to, let me write it in red. So the red part is r by r into r minus 1 to r minus 2 all the way up to r minus k minus 1. And the whole thing divided by, you'll have, and I'll only take this n minus m, I'll remove the n minus 2. So I'll get, let me write that in green maybe. So if I remove these two guys, let's see, we need to do that in blue maybe. If I take these two people, this person and this person, and what I get is n minus r into n minus r minus 1 all the way to n minus r plus 1 all the way to n minus r minus r. Let me erase it properly, write properly. It's n minus r plus 1 or minus 1, let's say, and then all the way to n minus r minus of m minus 1 minus 2. And the whole thing I'll divide by whatever is left. So left I'll write it in black. So what's left is the rest of the terms. So I have taken care of k factorial, m minus k factorial, n factorial. All left is n by n factorial. That's just the bottom part. Right? So that just gives you, so I'll split up into two parts. So I'll start with n into n minus 1. I'll go all the way to n minus k minus 1. Right? I'll leave this here, and the rest I'll write here. So n minus, n minus k. I'll go all the way to n minus of n minus. Okay, that's just this bottom part. So this is the green part. The green part. The green part I took care. This one, and this one. I wrote it as the green part. The red part I wrote like this, and the blue part was like this, and the black part I just wrote it like this. So now you're in business. So that means you've re-identified P choose K in this format. So let me readjust for you so you can see the screen properly. So P choose K is equal to R choose K by n minus m, and then this gave you this formula. Right? So let me just again adjust this a little bit so you can see the whole thing properly. So equal to this, and then I identify the red and the green term properly to get the answer. These also here, that's clear. So now you're in business now. See, now you know P choose K is this whole formula, right? So now once you know this whole formula like this, like I discussed last time, so you take these two things. Let's say you take three numbers. Let's use a different color. Let me get a different color, purple. So two different colors. So you take P to be equal to, let's say, R by M. Okay, you take P to be R by M. Very good. So now you look at P1. Let me look at P1. Let me look at P1. So a little different color. Let me go a little bit down. Okay, let me use same color. P1. So P2 is equal to. Sorry, right? So let's say P2 is equal to the other one, R minus K by N minus K. And let's say, so this is P1, P and P1, this is P1. And then let's say I take P2 in green, P2 to be equal to the upper bound. So it's R minus K by N minus N. Now you're in this state. So this whole thing is P of K, this expression that I have at the top. So now you can easily see, it's quite easy, right? You take the P of K, right? Essentially this expression right here. This is P of K, right? P of K. Now you can put two bounds on either side, right? So you leave the M choose K as it is, right? right? So leave the M choose K as this. That's on both sides. So M choose K is on both sides. Okay, M choose K. That's what this term is. It's M choose K on both sides. Okay. No problem. And then you write the two formulas down. So you look at each of these red over black and blue over black. Okay. So red over black, the red over black is going to be has K terms in it. The red over black is going to be less than at least P1 to the power K. So let me write that in black now. So let me write it in black now. Let me some other color. Let's see if I can find some other color, interesting color. Maybe light blue. Let's say. So the red over black, this particular term right here, right? This is always going to be bigger than, if you share it a little bit, so it's always going to be bigger than, each of the terms is bigger than P1. So it's because P1 is R minus K at the top and N minus K at the bottom. So N minus K is much larger and R minus K is much smaller than any of the terms. So each of the blue terms is going to be bigger than P1 to the power K. And it's going to be smaller than, on the other side, it's always going to be smaller than P because everybody is like R by N, right? So it's everybody's smaller than R by N. So it's smaller than P1 to the power. So it's P to the power. So it's, the blue term is like this. If you get another color, let me see if I can get another color. So I take this one, this one, yes. So I go take this person right here, right? This person right here is always going to be bigger than, if you stare a little bit, it's 1 minus P2 the whole to the power M minus K. Because there are N minus K terms, and each of them is bigger than 1 minus K. And each of them is less than on this side, if you look just a little bit, is this 1 minus P1 to the power M minus K. So that's how you just bound the upper bound and lower bound these terms, right? This term. And here also the same thing. So the bounds you get are very interesting. So now that's what I stated as a theorem last time. This is the theorem I stated last time. Let me write the theorem down so it's clear. So the theorem I wrote down last time was the following. I said that, so I don't know what you do, let's say theorem. I called it theorem 2.3.3. And I said that this exact description I wrote down. So I wrote down that this is a proof of this theorem. And this provides the theorem 2.3.3 from last time. Okay. So what does it give you? It tells you that P of K, the hypergeometric, is kind of close to binomial, but of course with different parameters on both sides. So binomial is not quite close by. So the idea is that, so the key conclusion is the following. So we made a conclusion. So conclusion, what's the conclusion? Is the following. So if M is much smaller than capital M, so relatively small, okay? And also M is relatively small to R. So the number of people with characteristic R is also much larger than M. Okay? And this would imply that both P1 and P are kind of close by. So there's no problem. Because M really doesn't matter. So P1 and P2 are kind of close by because M really doesn't matter. Because K is K is something between 0 and M, and this doesn't really matter. So once this is this, and let's say they're both approximately equal to P. So that means what you would get is P of K, P of K is like M choose K, P power K, 1 minus P power N minus K. That's what you would get. That's what you would get. And this implies that in this situation, when you have this this idea that this sample is much smaller than M, and the sample is much smaller than the amount of people with this characteristic you're trying to sample from, then what you would end up getting is that the key observation is that sampling with replacement is kind of the same as sampling. It means sampling without replacement. That's why in opinion polls and other things, you don't really bother. You just go and pick people up without replacement, but you assume it's with replacement. So you do without replacement sampling, But if the characteristic holds that m is much smaller than n, and little m is much smaller than r as well, you just go into you assume that the whole thing is independent, and then it will be minor. But this is the clear, correct analysis for width and null. So I'll make it. Let's go back again. Quickly recall. So with replacement means you have independent trials. Without means you have dependence. If you do the without formula, you get probability of P of k is equal to this, and that would imply P of k. If you do the algebra properly, it will all come out to be this. And then once you do that, you're on your way. So you just identify the bounds properly, and then you get this answer. But then you look at it, it doesn't look quite binomial, but it look binomial in the sense if P1 is same as P2, same as P2. Very nice. So that sort of concludes that that section of independence and dependent trials. So now I'll quickly move on to the next topic, where I will sort of formalize notation. So here I want to use a different color. Let's see if I can get the color out. See, I want to use maroon. Very good. Yes. So in this section, what I will do is I will now start on chapter 3, which is discrete random variables. So, so here I'd like to do the following. So here the whole idea was that we had these Bernoulli trials, and each time we created new sample spaces. So if you noticed, we had various experiments. Giving rise to Bernoulli trials. And also dependent ones that we check. But each time we created a new sample space. Right. So this is kind of a sample space for a new distribution. So which means that every time I gave you a hypergeometric, I went and said, okay, I have sample spaces this, Poisson, I give another one, and so on. So now this is something that's a little inconvenient. Can we do all this in one sample space? Because you don't want to change this. Okay, the question I want to ask is that can we do all this on one sample space? Right, rather than keep on going and changing different things and sort of so the jump is from this is to do this. So one needs to construct a certain concept called random variables. So what you do is you define functions on the space. So idea how to do this is you define functions on the space. So functions on the space that describe the output, whose outputs relate to the question under consideration. So that describe the output of interest. And once you do this, you're on your way. So so these are called random variables. They're called random variables. That's the formal idea. That is, your random variables are brought into the picture because you want to work with only one sample space. You don't want to work with many sample spaces. That's how you sort of start. So, okay. Let me just do a quick example, and then I'll try and illustrate the idea of random variables in a quick way. Yeah, maroon is gone again. So let me do example. 3.111. So here, what I want to do is I want to just set up this framework properly. That is, I want to set up this framework properly. So how do I do this? Let me go back to black. And then here, what I say is that suppose a coin is flipped. Let's say maybe 3 times. I flip it 3 times, and I want to know the number of heads in 3 tosses, or I want to know the first tosses. So let's say 2 questions. 2 questions. Question 1 is the number of heads in 3 tosses. That's one question I have in mind. Question 2 is I want to know is that the trial at which the first head should. So the trial, if it exists, at which here is this, at which first head should go. Right. So now this is something we have to think about. So you know how to do this. So you just what do you do before? You would write the sample space S as H H H H H T H T H and then H T T and then write the whole thing down as the other one T H H T H T T T H and then T T T and then you have these 3 samples, 8 sample points, and then from this you try to understand the question. So then what you would do is you would try and pick the number of outcomes that have 3 heads or number of heads. You just write them. If you want to say, okay, 2 heads means you go pick the outcome that satisfy 2 heads and compute the whole thing. But let's just do a simple calculation. So now, suppose I say, let's define the function x. Okay. X is a function from sample space f to 0, 1 or to let's say 0, 1, 2, 3. I define x in the following form. I define x to be what I do is take a point x and I just count the number of x. So what I do is I rewrite this a little bit. So x of s is this. So let me start with this a little bit. So select. So I define it like this. So I define, let's say, y as the s from 0 to, let's say, 0, 1 can occur the first trial. So y I want for the second question. So I say y is, let's say, 1, 2, 3, or I say I use the null notation called none, the alphabet notation none, by y of s is the trial at which head appears in s. There are 2 functions that define. So once I do this, let's do a little table. Let's see if the table comes out nicely. So let me do a table. So the table is quite clear, right? So I do this, and then I do this, and I do this. So I first write down the outcomes of S in this column, right? So let's call that as little s. I have H, 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 T, H, T, H, H, T, 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 H, H, T, H, T. Erase the bottom line. Second, I have to go THH, TTH, and then TTT. These are the 3 columns I have. And I go down all the way, fix this, very good. Then on this one, I plot the values of x. So x of s, so I go here, x of s, let's go on x of s. Then what I do is I go here and I plot the value of x of s. This is in green, like I said before, and maybe x of s is x of s, and this is y of s. Right? So in this case, x of s is 3, right? X of s is 3, right? In this case, it's 2. In this case, it's again 2, 1, 2, 1, 1, and 0. And here the number of trials at which the first trial at which it appears is 1, 1, 1, 1, and then here it's 2, here it's 2, here it's 3, and here it's none. Okay. That's how I would fill the table. So now, if you want to know the probability of, let's say, from this question, if you want to know the, let's keep this page alive. From this, if you want to know the probability of, let's say, 2 heads in 3 tosses, right? So what you could do is, you could just go and see the elements of S for which x of s is 2, right? So that's the same as saying you look at the inverse image of x when x is 2. Right? And that, if you look at this equation, right, if you go to look at the table, it's just the probability of the event, let's say, HHT, HTH, and that's the 2 event, and then the one more, TH. And if you do this properly, this calculation properly, it's just going to be again 3 by 8, and that's the answer. So I didn't have to go and, okay, this is how I do the calculation, but I could use my x to get the answer. So one way in which I could write. Let me erase this. Let me write this in green. So this is the same as x inverse of the set 2. Like 2 and curly brackets and 3 are all the same. Very nice. Very good. That's what it is, right? So very good. So now you're on your way now. So now you understand exactly how to do this. Similarly, you can do the the thing of probability. Let's go to the next page. Let's do the next one. So let's say you want to know the probability that head occurs in the first toss. Right. That means that's the same as the probability that y inverse is 1. Right. You look at the first one. So that you know, again, you go back and look at the sample space, and that's the same as the probability that y occurs first toss means you have HHT, HHH, HHT, HTH, and HTT. These are the 4 points, and the answer is just 4. And that's just how. So once you do this whole calculation, okay, this calculation we had to do by hand, but let's summarize. So what you would get is the chance that let's say I'll write this as x equal to 0. That means there are no heads is going to be equal to 1 by 8. You can do it. Okay. The chance that x equal to 1 we just calculated, didn't calculate x equal to 2, it's 3 by 8. X equal to 2 is 3 by 8 like we did before. Sorry, let me erase this. It's 3 by 8. I'll remove this since I've discovered this new trick. The chance that x equal to 3 is just again 1 by 8. So I won't say similarly. One can proceed. One can, I just say summarize. I say similarly. One can calculate the other problem. And similarly, you can do for the y also. You can do the same thing. You can say y equal to 1 is which we already done is 1/2. Probability y equal to 2 is the same as 1/4. Probability y equal to none. Y equal to 3 is like 1/8, and probability y equal to none is again 1/8. So that's how you finish off the problem. So what you notice is that these two equations give the complete distribution of x and y. X and y. So, in some sense, what does this line mean? What does this line mean? What I mean by this? So it describes how x and y distribute the probabilities on their respective ranges. So in a sense, what I mean by this line is that they describe how x and y distribute their probabilities on their distribute the probabilities on their respective ranges. That's what this is telling you. So this is one setup where you use functions, and we sort of forgot about the original sample space. We looked at what the functions do, and you can just look at the range of the functions and understand their probabilities. And once you know that, you know exactly what x is doing, what y is doing, what the range is, what the probabilities are. You can answer your questions. And essentially, you've forgotten about the sample space, sort of in the background. Once you know these two equations, of course, computing these two is a little hard, but as a math. But you have to do it only once. Okay. So that's what I did. So I had this two questions in mind. I constructed two functions. I did a table. Then I want to construct the question I have an interest is 2 heads and 3 tosses. That's the same as x inverse of 2. Then I go down. I want another question. Let's say head occurs in the first toss. That's the same as y inverse of 1, and so on. So maybe I'll just say here instead of head occurs, I'll say first head occurs. So now this structure we can formalize. So how do you formalize the structure? Let me go here. So here you can formalize. The formalize is the following. So let's do a theorem. Theorem 3.1 point. Do any definition before that? Maybe not. It's not there. Let's just do a simple 3.1. So what's the model? So let S be a sample space. With probability P. And let X be a function from S to T. Yeah. Then X generates a probability Q on T given by the Q of any set B is given by the probability of X inverse. That is the set of all sample points for which X is live inside. This is a nice term. So the probability Q is called the distribution of X. So that's how X distributes its values, distributes probabilities onto its range. That's what we do. Since it describes the probability S, probability of, so describes, I don't know how to do this, sorry for that, it's copy. So it describes how X distributes the probability from S on. Oh, so maybe I'll take a quick 5-minute break and I'll come back and try and show in the next class. I'll try and show this theorem 3.0.